Hello everyone. In the previous pre-lecture video, you saw how you can approximate the value of a function at one point. But did you know that you can find the exact value of the function with Taylor series? In this video, you will learn how to compute the Taylor series representation of functions. Sometimes we also call them Taylor expansions. Remember that a power series has this form: the sum from n equal to 0 to infinity of Cn times x minus a to the power n. We call a the center of the power series. The idea for computing Taylor series is similar as for Taylor polynomials. But in this case, we want to represent the function with a series that matches not only the value of the function at the center, but also the derivatives of all orders. Let's choose an easy example to start. We want to find the Taylor series of the function f of x equal to e to the x with center at a equal to 0. Therefore, we need to determine the values of the coefficients Cn. These are the steps that we will follow. With center at 0, the Taylor series has this form: e to the x equal to c0 plus c1 times x plus c2 times x squared, etc. Now, we evaluate the expression at x equal to 0. We can observe that 1 is equal to c0 plus the sum of zeros. Thus, c0 is equal to 1. Next, we take the derivative, and we evaluate at x equal to 0 again. We can see that we obtain that 1 is equal to c1 plus the sum of zeros, so c1 is also equal to 1. We repeat this process with the second derivative. In this case, we obtain that c2 is 1/2. By repeating this process with the third derivative, the fourth derivative, etc., we obtain the corresponding values for the coefficients c3, c4, and so on. But we cannot do this forever, since the power series has infinitely many terms. Thus, we will try to find a general expression for Cn. Let's pay close attention to the expression of the nth derivative. We can see that 1 is equal to n times n minus 1 times n minus 2, etc., times 3 times 2. Multiplying the left and right-hand side by 1, we obtain that 1 is n factorial times Cn, or equivalently, that the coefficient Cn is 1 over n factorial. Remember that 0 factorial is equal to 1, so the expression for C0, 1 over 0 factorial, is well defined and matches our previous calculation. Finally, we conclude that we can write the function f of x equal to e to the x as the sum from n equal to 0 to infinity of 1 over n factorial times x to the power n. This is the Taylor expansion of f of x with center at 0. Of course, the expression of the power series will change depending on your choice of the center. For example, for the function f of x equal to e to the x, when you choose the center equal to 1, you obtain the expression you see on the slide. Observe that the coefficient for Cn changes, and now it is e over n factorial. Oh, and be careful. Sometimes the Taylor series might not be equal to the function that it represents. But we will leave that, all the details and difficulties for the lecture. However, in general, we have the following result. If f has a power series representation or expansion at a, then its coefficients are given by this formula: Cn equal to the nth derivative of f evaluated at a divided by n factorial. Provided, of course, that the values of x are within distance r from a. This r is the radius of convergence that you need to determine. With this formula, you can easily find the coefficients of a Taylor series. To illustrate the theorem, we go back to the previous examples. In this case, when f of x is e to the x, and when we choose the center at 0, we have that the derivatives of all orders are equal to 1, and we obtain the coefficients 1 over n factorial. For the same function, but with center at 1, we have that the derivatives of all orders are equal to the number e, giving us the coefficients e over n factorial. In both cases, we also have that the function is actually equal to the Taylor series. Can you figure out why? In addition, we observe that the value of the derivatives is constant in both examples, but this is not the case in general. The values of the derivatives will depend on the function that you want to represent with the Taylor expansion. Now, as an exercise, try to compute the Taylor expansion of the cosine with center at 0. See you in the lecture.